Hello viewers, today we are going to discuss evaluating the area of one type of quadrilateral, the trapezium, using a geometrical interpretation. Usually we do this algebraically, but I would like to present this geometrically. A trapezium is a quadrilateral in which one pair of opposite sides is parallel and the other pair is not. It looks like this. If the dimensions of the parallel sides are A and B and the distance between the parallel sides is h, then the area of this trapezium is evaluated using this formula: half times the distance between the parallel sides, which is h, times the sum of the lengths of the parallel sides. So we are going to prove this geometrically. So here we go. We are taking two trapeziums. Actually this is one trapezium. Let's say this is the length A, this is the length B, and this distance between the parallel sides is h, right? This is a replica of the same trapezium. I'm just going to take it over and flip it like this. Okay, so bingo. What do we have here? We have a parallelogram actually, because these two sides are already parallel and these two are also parallel. We'll prove it how. And therefore we actually have a parallelogram whose side or the base is A plus B and the distance between the parallel sides is h. So the area of these two parallelograms, the area of these two trapeziums put together, that is twice this area of the trapezium, that would be A plus B times h. Or in other words, the area of the parallelogram which is twice the area of each trapezium, that is A plus B, which is the base of the parallelogram, times the distance between the parallel sides, which is h, or A is half the distance between the parallel sides of the trapezium into the sum of the lengths of its parallel sides. That's an interesting way to look at this, isn't it? Now, to make this proof a little more rigorous, how do we know that we actually get a parallelogram? So let's say this angle were phi and this angle were theta. Because these two sides are parallel, one of the basic properties of parallel lines is that there is a transversal cutting a pair of parallel lines. We know that the sum of the co-interior angles is 180. So this needs to be 180 minus psi and this needs to be 180 minus theta. Now we are taking this parallelogram and trapezium and flipping it over. So we get this figure. Right? So this would be 180 minus theta and this is theta, of course. This is flipped over, so this is A and this is B and of course this is H. Now you have 180 minus theta and 180 minus psi on the same side, so 180 minus theta goes here, so 180 minus psi is the angle here. And of course, theta and psi are the angles on the same side of this trapezium, so here also it needs to be the same. You're just flipping it upside down, that's it. So now we look at the sum of these two angles. This is psi and this is 180 minus psi. That makes it their sum 180, and similarly this is 180 minus psi and this is psi. Their sum is again 180. So this proves, in addition to these lines which are obviously parallel, that these lines are also parallel. That's why we get a parallelogram. Hope this is a nice and a unique way of looking at this derivation. Thanks for watching. Subscribe to our channel for more interesting videos.